Hello everyone, I'm Toshihiro Kamishima. This is a joint work with Shotaro Akaho, Yukino Baba, and Hisashi Kashima. This is overview of our talk. We propose a new desirable property for bias-aware classifiers, stability. This work is preliminary, and its objective is collecting datasets to examine the stability. Cognitive bias used as a proxy of the sensitive information, and we collected preference data by using crowdsourcing. After showing bias-aware model, we test its stability. However, contrary to our hypothesis, the model was not stable, and we discuss the reasons of its instability. We begin with notations. S denotes a sensitive feature, representing information that should not influence the prediction results. In this work, this represents whether or not an item is more preferred due to a cognitive bias. Y denotes a target variable, representing a predicted class, whether one item is more preferred to the other in this work. X are non-sensitive features, representing all the information that is not represented by S or Y. In this work, they represent a pair of items shown to the subjects. Finally, we use the statistical parity as our fairness criterion. This criterion is the statistical independence between S and Y, meaning no information about S influences the decision Y. The objective of a bias-aware classifier is to learn the most accurate predictor while satisfying a fairness constraint. Formally, the loss function is minimized under the fairness constraint. However, here is a big problem. The loss is evaluated on a biased dataset, but the loss should be evaluated on an unbiased dataset. We need the other desirable property for bias-aware classifier, other than maximize accuracy on a biased dataset. Recall that bias-aware classifier removes the influence of S on Y. Therefore, if two datasets consist of the same information, except for that represented by S, a bias-aware classifier should run the same models from these two datasets. If the classifier has the property, we call the classifier is stable. The objective of this preliminary experiment is to make a dataset to examine the stability of bias-aware classifiers. A main task is a paired comparison task, choosing the more preferred item from a pair of items. We collected these preference data on a crowdsourcing service. As a proxy of a sensitive feature, we use a cognitive bias. The factors of a user interface that influence the subject's choice. We hypothesize that if the same models are learned from datasets influenced by different kinds of cognitive biases, the bias-aware classifier is considered as stable. We tested two types of cognitive biases. The first cognitive bias is a positional effect. The item displayed near the upper left corner of the interface screen is more frequently chosen. We tested two types of assignments of items, baseline and fixed. In the baseline case, the positions of items are randomly assigned. This is regarded as an ideal randomized control trial. In the fixed case, the positions of items are affected by the popularity of items. The second cognitive bias is a bandwagon effect. The item indicated that other people prefer is more frequently chosen by the subject. We use an interface indicating popular item like this. In this case, the items indicated as popular are irrelevant to their true popularity. We check whether or not the collected preference data are influenced by cognitive biases. In this case, S is an intervention and X is a confounder. In this experiment, because the selection of candidate item is randomized, the causal effect from S to Y can be measured by the formula. Experimental results in the table show our datasets are influenced by cognitive biases. We move on to the bias removal techniques. This is a model for estimating the influence on Y while removing the influence of S. In this case, S is treated as a confounder instead of X, and X becomes an intervention. In this model, there is a backdoor path through S, and this can be removed by a stratification technique. This is sum of effects of X on Y per strata, and the weights of strata are proportional to their sizes. We'd like to note that stratification technique has connection with a generative type of fairness-aware model. The second line is a joint distribution after imposing a constraint of independence between Y and S. As in the third line, this can be considered as the stratified effect of Y on X, whose direction is an inverse of the previous stratification. We hypothesize that if a stratification technique is stable as a bias-aware classifier. Similar models would be run from three types of datasets: random, fixed, and bandwagon. For each dataset, we computed these probabilities. If our stratification technique is stable, these probabilities would be similar. However, the difference between random and bandwagon cases is rather large. This experimental result indicates that, contrary to our hypothesis, the stratification techniques are not stable. We built two types of hypotheses why our technique was not stable. First, cognitive bias may not be fully removed by the stratification. Because the scheme of data processing might change the causal structure, we will explore another type of causal structure. Second, confounders other than controlled cognitive biases might exist. Because we showed popular marks relevant to its real popularity, this might cause another type of cognitive bias. We plan to collect data influenced by the other cognitive biases, such as a memory effect. Our contributions are as follows. That's all we have to say. Thank you.